You started talking about binary trees, and generally a binary tree, it's kind of useless because if you want to build a binary tree, the first question that you will have will be, okay, where do I insert a value? Now, if the binary tree is empty, it will be the new root. And after that, maybe you will get a second value. And now you have the question, on which side? Is the right sibling or the left sibling? Okay. And these questions will continue. So generally, yeah, or left. So you will always have this question, right or left. And after that, what do? You move to the next level or you fill up the current level. Okay, so if you just take a binary tree, you'll have a lot of questions in order to decide how do you insert, and after that, how do you delete. So a binary tree, just a binary tree, a simple binary tree, it's useless because it will generate a lot of questions. And in the end, if you decide some rules that you will follow in order to insert or delete or search, you will have a binary tree with a specific set of rules. So at that point, you can name it. It's not just a binary tree. It's a binary tree with those rules, and you can name it, or others have already named it. So when we talk about binary trees, we will always take specific binary trees. And we have seen a type last week. Even if we don't implement the solution using a common binary tree structure, we used an array, but the discussion was all about a special binary tree, a complete binary tree. And you have seen what are the rules. Every time you fill up the current level from left to right, and after that you switch to the new level, new row, and so on and so on. So you have a complete binary tree. Okay, so this is the problem with binary trees. You need some rules in order to follow, in order to do something with that. Okay, so a complete binary tree, the story from last week, was very useful in order to understand a heap or a priority queue. Okay, because a heap is implemented or is designed as a binary complete tree. And because you have a binary complete tree, you have seen that there are those special relations between the location in an array of a node and its parent node and also its siblings. So we have the formulas that we have defined last week in order to determine if that binary complete tree was to be stored in an array. Using those formulas, we can easily determine where is the parent of the current node or where are its siblings, the left or the right side one. Okay, and that was very helpful because even if the story was designed as a binary complete tree, the implementation was quite easy using an array, a static array or a classic array. Okay, so today we move to a new type of a binary tree, which is very useful for only one operation, and that's the search operation. So if you have a large set of values and you want to search into that, if you use an array, you have what? Sequential search, which is the, let's say, the slower, and it has the biggest complexity because the sequential search in an array has the complexity equals with n, where n is the number of elements. Why? Because in the pessimistic scenario, if you search for a value in the array, in that pessimistic scenario, that value could be the last one. So you need to do n comparisons in order to find it. Okay, or to conclude that the value is not there. Okay, now after this will be a benchmark. Okay, from this point you have new algorithms which are faster and faster, but they also have additional criteria. So one of the fastest searching algorithms in an array is the binary search, but the binary search has the problem, or it has an additional requirement, that the array should be sorted. Okay, so because in that way you split each time the array into two, you check where is the value that you are searching for by comparing it with the middle value, with the median value, and after that you continue the search in either the right or the left half until you find the value. Okay, so that's the binary search. And after that, you have other ways to do it. But let's say that's the one of the fastest algorithms for searching in an array. But with the additional condition, the array should be sorted, okay? Because otherwise it will not work. Okay, so we have a searching for values is a problem. It's a common problem, okay? Every time you search for something, okay? And we need a data structure that will help us with that, okay? So we know what are the limits of an array, and we know what are the advantages of dynamic structures like simple linked list. So in that case, can we use a dynamic data structure for that? And this is the scope of a binary search tree. And that's why it's called binary search tree, because its only purpose is to help you search for data. Okay, so this will be our example for today. Okay, and once again, let's add the standard libraries that we will use through this example. Okay, and here we have include malloc and maybe string.h. Okay, so a binary search tree is a data structure which is very similar with a simple linked list, or let's say more similar with the double linked list, because it's a dynamic structure, which means it can grow with any sizes, and it's very efficient at this. Okay, so it's not like an array, you need to resize it, copy the values. It can dynamically grow. And here, each node, and that's the difference from let's say a simple linked list, each node, instead of having only one address, only one pointer to the next value in row, here each node has actually two links, two pointers. One is named the right side link, which generally points to the right side sibling, and the other one is the left one. So if we would define the data structure for a binary search tree, the node will look like this. Okay, so let's say this is a binary search tree node, binary search node, BS node. Okay, and here I will start with this feature, which is important for binary search tree, which means we have two pointers. So one, let's call it right, and the other one, let's call it let's see, what's the problem? Okay, are you going to do the iterative version of the traversal? No. So let's establish this. I will generally try to not do anything iterative with binary search trees or graphs. Now, if you want to try to do that, and maybe you will get to the same conclusion that I got several years ago, that it's a waste of time to do iterative traversal. Maybe the only argument that I will choose an iterative traversal or searching is that maybe I don't have enough memory, because if you use recursion, each time you call the same function again and again, you eat up memory. So if I need to do a binary search on a microcontroller that has only, I don't know, several megabytes of memory, and generally in those cases, it's forbidden to do recursion. So it's in the project specs. No one will allow you to do that. If they will see you are doing recursion, I don't know what you'll be punished for that. You will not get any bonus, for example. So in that case, yes, I will try to do the iterative. But now trying to do a binary search tree, implementing a binary search tree in a microcontroller is once again wrong by definition. Why are trying to do that on a limited device? Maybe you should connect to the server and do the search there and get the results. So the iterative version for this kind of structure is like, I don't know, it's like trying to do a multiplication with addition. Okay, try to do everything with additions. We know it's possible, but why to do it? So starting this example, so thank you for the question, everything will be done in a recursive manner. Now, if I really will want to give you an assignment that will take some time, just to be sure you stayed at least 5 or 6 hours in front of your computer, that will be a reason to ask you to do an iterative implementation. But other than that, no. Okay, because it's not efficient, and sometimes it's even more difficult. So I think if you try to do a delete in an iterative way, this is like giving you a subject that no one will do during the exam, even if the exam will take, I don't know, 5 hours. So yeah, no. So I will try to avoid the iterative because we don't have time. It will be like we start writing a function at 5 o'clock, and around 7 we are still adding ifs. If that, yeah, but we didn't cover that. Okay, let's add another if. And if you have more than one if, that's your path to a possible disaster. At some point, it's like we will be tangled between those ifs. So yeah, everything will be based on recursion. Okay, and if you have issues here, this is something you should recap. Okay, so thank you for the question. I think we clarified that everything will be in a recursive manner. Okay, left. So I have right, left. Okay, now another argument for recursion. If you are still afraid that we don't have memory, what's interesting is that if you go into a binary search tree, actually the number of recursive calls is generally equal. So the height of the call stack of that recursion will be actually equal with the height of your binary search tree. And we know that generally that's not an optimum, but yeah, maybe we need a balanced binary tree. Yeah, so a binary search tree can lead to a height equal with n if you give all the values in a sorted way. So yeah, you will have quite a high call stack, and that's not okay. It will eat up a lot of memory. But if we will cover balanced bit binary trees like AVL, then you will have the maximum height is logarithm base 2 out of n, which is still a very small value, even if n is equal with millions. Okay, so in that case, recursion is something manageable. Okay, so we started with the definition by defining the two left and right pointers, okay, to the left and right siblings. And now you need to store the values, okay? So let's do something that, let's define a structure that we will store in a binary search tree. So for example, I want to search for, I don't know, let's say product. I think we, at some point we did that. So here, I want to search for to store the products in a catalog and be able to search fast for a product. So starting with heaps, we introduce this new concept, okay, regarding searching or regarding values, or also in hash tables, starting more specific with hash tables. The concept of searching for a entity by a value, and we name that value a key. So every time you want to implement a structure for searching or an algorithm for searching is always related with the keys, okay, with values for which you search. Now, keys can be unique, or the data structure can accept multiple values with the same key. In terms of binary search trees, there is this property which is saying that the key should be unique. Okay, so this is something which is related with binary search trees, okay, or with search trees. The key is always unique, because otherwise that will lead to situations where if you allow that to happen, to have multiple values with the same key, they will be somewhere in the tree, but when you will search for that value, for that key value, you will always get the first location. And you will never know that there are also other values with the same key after that first location. You will always get that first location. So that's why it's not allowed to accept the fact that you can insert multiple values with the same key in the binary search tree. Okay, so if you want to store the product in a binary search tree, the first thing that we need is something that should be unique for each product. And that could be what? A barcode, for example. Okay, and we play with this, or a code. Okay, so even a string can be a key, because we can compare two strings by using string compare. Okay, remember, string compare returns 0 if the values are equal, -1 if the first one is less, and +1 if the first is greater. Okay, so you still can compare strings with string compare from string.h. Okay, so we can use either an alphanumeric key or a numeric key. That should be not an issue. Okay, now a product may have what? A price and maybe a stock, available stock. Okay, so in this case, if I want to store in this binary search need, so it's like a catalog in which I want to search fast for products based on barcode or code. We can decide this when we implement insert. Okay, and because we want to get the price or the available stock. So here I will say product. Now, this is one utility of a binary search tree. Okay, generally to use it as a data structure, use both for searching and for storing data. Now, another utility for a binary search tree node, and that's the definition of an index, is not to store the data, because the data can be huge in terms of memory. Okay, and if you store that index in memory, it will eat up a lot of RAM. And we know that if you need to store something, a large volume of data, the only place built for that is the hard drive. So in that case, if you want to use an index, so, okay, so in this moment, this is a data storing and searching structure. And this is okay for small amounts of data, okay? I don't think for millions of billions of products, for, I don't know, hundreds or thousands of products, okay? So this is a data storing and searching structure, okay? It can be used for both. But if the volume of data is too big, you can't store it in RAM. You need to store it on the hard drive. So in that case, a binary search tree can be used as an index. So let's suppose these products are stored in a file. So if I will define a structure as an index, so let's say binary search tree.
What do you mean by a structure as an index?
I will define it and we will continue the talk from here, okay? So if I will define the data structure to behave like an index, okay, so just wait 1 minute to define it, and after that, maybe it will be clear what I'm meaning. So okay. Binary search index node, okay? In this case, once again, these are specific to any binary search tree. So it doesn't matter if you are using the data structure to store data or to use it as an index. This is what's different. You don't store the data, you store what? The code or the key, okay? And here you have a long file offset or file location, okay? So let's say this is product code or product barcode is the key here, product code. Okay, so this is the key associated with the value itself. Now, a product may eat up 1 kilobyte, but you see here when you use it as an index, and you ignore the 2 pointers because they are also present here, an index will generally occupy a very small amount of memory if you compare it to the product itself. So let's suppose the product here is, let's say, 500 chars. So we have 500 bytes, a 4 byte int, a 4 byte float, and another 4 byte stock. So here you have 512 bytes, okay? So here, each node will have those 512 bytes plus another 8, 4 plus 4 here. So you have 520 bytes. And that it's half of a kilobyte, for example. So try to see what's the amount of RAM that you need in order to store 1 million products in this data structure. Okay, so you need a lot of RAM just to store it. Okay, and if you increase that to 1 billion products, the size will be even more bigger. But here, you will store only the code. Okay, let's say only 4 bytes. This could be a 8-byte integer. Let's suppose it's a long integer, a long. Okay, so here you have only 12 bytes, okay, associated for each product. And if you compare that to 512 bytes, the difference is huge, and that will matter a lot for millions of products or billions of products. So at some point, you can store this in memory, but you can't store this. So large volumes of data are stored on the hard drive. Now, what's the difference between these two structures and why I named this? So this is a data index structure. Because if you want to get the name of the product, if you want to get the price, if you want to get the available stock, here, you just need to find the product and you have it. It's there, it's in RAM, you already have it, it's in memory. But here, the only scope of this data structure is just to tell you where to look for the product details on the hard drive. So the index will be in RAM in order to search fast into that, but the data is on the hard drive. And this is the relation between two, this offset here. And now if you go back and remind yourself how you can use a binary file, there you can store data as variable length data. So each product will occupy an amount of bytes equal with its data. So there you can do only sequential search, or you can do a direct access binary file. Okay, so in that file, you need to be sure that each product, not mattering what is their data, they occupy the same. For example, you extend all the products to the maximum size, 1K. So you know that each 1 kilobyte in that file is actually a product. And knowing that, it's easy to jump by 1 kilobyte, and to reach different locations in the binary file. So these are the two ways that you can store data in a binary file. Either by extending everything to the same size, or by storing each element with its own size. Okay, so it has advantages and disadvantages, but generally I will go for a direct access binary file. So you see here, the index will help us search fast through 1 million products based on their code. And once I find the product, I know where the data is in that file. And this is actually a database. So every time you are using a database, a MySQL, Postgres, Oracle, SQL Server, whatever, any database, okay, this is how they store the data. And that's why when you define a table and you define a primary key, that's an index, and the database will load the index into memory to speed up the reading of that index, to speed up the search by a unique key. And after that, it will deliver you the data from a file. Okay, once it has found where the data is in that file, using this file offset, which is the location of that data in the file, it will retrieve it to you. So a database is actually a combination of an index and a file. Okay, that's why you have at least one key there, because otherwise it's like playing with the files directly, and that's very slow. Okay, so it's clear what's the difference between a data storing and searching structure and a data index structure. This is only for searching. Okay, which means you don't store the data here, only the key. And generally, you need other values associated to that key. Okay, so it's clear what's the difference. It's okay. Yeah, let's see. Okay, so that's the difference. Now, in practice, which do you believe is the most common approach? This one or this one? In any software, which do you think it's the most used approach? The first one or the second one?
The second one.
The second one, yeah, because exactly, the one with the hard drive. And this is, let's say, useful only if you know that you have limited data. But we now live in a world where we have more data that we can process. Okay, now this is the biggest issue today. The data volumes are huge. Okay, we don't have, or the computing power that we have today is still struggling to process that huge amount of data that we can collect at any minute, any hour. Okay, so today is not a problem to record. There were experiments several years ago, and you can have we were talking about a webcam. You can have a webcam or a GoPro camera attached to you, and you can actually, and this is something you can do, you can actually record your entire life. Okay, you can store that in the cloud, and it's quite cheap, so you can actually record your entire life, whatever. And there were different projects conducted in order to prove that this is possible. Now, the only thing that you need in order to make that a useful product is to have the ability to search into that. Okay, so you have a cloud storing your entire life, whatever you are seeing is stored. But now the biggest issue is how do you identify objects and you search for them? Okay, because this is like, I have my personal assistant, it's recording everything that I'm seeing, and I want to search for my keys. Okay, you don't need to ask your, I don't know, your companion, where have you seen my keys? You go there and ask your assistant, hey, where is the last time I have seen the keys? So it will search through all the recordings and it will say, hey, you left them there. Okay, I just saw them. But storing the data for this kind of a project is now something you can easily do. Okay, so this is doable. Okay, so okay, now so you have seen the two utilities, the two ways of storing this kind of stuff. The difference is just here. Okay, now in terms of inserting, searching, and deleting, the operations, the algorithms are the same. You don't have different algorithms for these two approaches. The only difference is that when you find the key here, you will actually get the offset, and after that open the file, jump there using file seek, for example, and retrieve the data. Now here, when you find the key, you already you will find the product. So this is the only difference. But in terms of inserting and deleting, the algorithms are the same. Okay, so we have these two data structures. Okay, and now let's continue. So what we want to do is to create a binary search tree. So the first thing that I want to do is to have to be able to init the product. So let's do this method, and it's returning a product, init product. Once again, we don't have a dynamic field here. So
can we change the field so that we can have a dynamic one?
Yeah.
If that's okay with you.
Yeah. For me, it's not an issue. You can choose. So
let's have an example.
Okay. I think we had last week or 2 weeks ago, but I can alternate. Okay, 1 week without one week with. So let's go for a dynamic field here, or just keep them both. I think it's even better. Let's have so let's keep this as a static array, and let's make this one a description. So now we have it both. Okay, it's a dynamic and a static one. Okay, not a problem. So let's init the product. So what we need, we need a barcode, a description, a code, price, and stock. Okay, so let's do that. So const char barcode. Remember, even if you have static or dynamic arrays, strings or arrays of values, always pass the input arguments as pointers, okay? So be generic here. Const char description, okay? And float price, float stock, and code. Okay, so we create a product, an empty product. And what we want to do now is to initialize the data. Now, once again, don't forget to set defaults here. It will save you from a lot of trouble. Okay. If you forget to initialize them later. So when you define the data structure, give also default values. It's a small thing that you can do here, but it has great value later. Okay, so just to be sure, and especially pointers, make them null, because otherwise you will forget later. You'll be focusing on the algorithm, you will have other things to worry about, and you will forget about this simple stuff. Okay, and also here, if you will go for this one. Okay, so here I define the product. So let's say code equals code. I will always start with the easy part. Product price equals price. Okay, product stock equals stock. Okay, now let's switch to the strings. So for the static one, I need to copy it. String copy product barcode and choose the barcode. Okay, and for the other one, we need to create space before copying. Okay, so that's the main difference between a static array and a dynamic one. The second one requires space. So here I would say product description equals new, char asterisk malloc. So here I will have string length of description +1, everything multiplied with size of char, okay, which is 1 here. Okay, and now the string copy. So string copy product description and description. Now, because we have a dynamic field, remember every time or in many occasions, we need to copy an article from an input argument to the data structure location, for example. So in order to do that, if you don't have dynamic fields, you can use equals. But if you have at least one dynamic field, and now we have it, this is the description, you need something similar with the equals operator from C++. So you need to create a function for that. Okay, so we need it because otherwise equals will create shallow copy. Okay, in this case, and we can easily get into dangling pointers because we will try to free up memory. So that will lead to very strange runtime errors. Okay, so what I need here is a function. Yeah.
Are we supposed to do that, or can we like work faster even if we shallow copy?
Now the risk is that what will happen if during the exam you do shallow copy, and I don't know what you will do. You will find in a situation, maybe you insert in a list or insert in a binary tree, and when you test it, you will get strange behavior. So it's a risk. If you, I don't know, if it's a manageable risk for you, you can do that, and maybe we will not observe that. Okay, but it's a risk, and at some point, and you know Murphy laws, so I think during the exam the worst will happen. Okay, you can be lucky 99 days of I don't know, on a year, but if the exam is in the 100 day, then you will, I don't know, you will find yourself in the worst scenario. So okay, now if you can manage that. Sorry?
But this time, aren't we creating a new areas of space? So we're shallow copying, but if we're shallow copying here, Like
Yeah.
if we're returning a new product, it's okay.
Yeah, here it's okay because
Here, yeah, okay.
there is this point when we need to do it. Now, the problem
Yeah.
is when, let's suppose we insert a product in a node in the binary tree. So there you will have a product which could be in heap. And if we copy by using equals into the node, and after that you destroy the product, okay, you will have a node with a product that has the description pointer referencing something which has been released. So if you just print the array, it will crash. The tree, it will crash, okay?
Yeah, I understand. I was
Yeah.
just talking about this
Yeah,
one.
but here it's okay because here we do a shallow copy, but we know that when this stack will be destroyed, no one will release the space. If you do this here, that's another story. This is like shooting your own foot. So if you do, I don't know why you should do that. Okay, description, that's another story. Here you do a shallow copy, but you also release the space. So try not to do that, especially here if the method is called init or create. But this in the end will be a shallow copy because here we will have an equals. Okay, so we need another method to copy a product to another copy. So let's say copy product. And the destination, this will be like string copy, okay? So the destination, it's a product, but I know it will change. So this will be the destination, product, let's say destination, and this will be the source one, source. So in this case, we need to copy into here. And in that way, we will also try to avoid the memory leak because we will change the address there. So destination code equals source code. Okay. Destination price equals source price. Okay. Destination stock equals source stock. For the static array, we use the standard string copy. Destination barcode from source barcode. Okay. Now this is the reason for this method. So we want to remove the possibility that we will create a memory leak. So if destination description is different than null, release it. Free destination description. Okay, and after that we need to create space again. Description equals malloc string length of source description +1. Okay, and string copy destination description source description. Okay, so now we can easily copy a product into another copy without worrying about the possibility that at some point you will have two products sharing the same description. One will be released, okay, it will free up that memory, and then the second product will point to an address in heap which doesn't belong to you. And from this moment, every time you want to use it, you will get a runtime exception because it doesn't belong to you anymore. So that was the definition of a dangling pointer. It's a pointer with a number, it's an address, it's not 0xCCC or null, but the address doesn't belong to you anymore. Okay, so you don't have read and write access there. Okay, so in this way, we know how to copy the product. So we know how to create a product, we know how to copy it. In order to test the solution, we need a print product method. P. Okay, and here I will have printf. Now, if you have dynamic fields, once again, try to check if the address is not null, because otherwise printf will crash. Okay, so let's say now I'm I'm printing product with ID equals %D and barcode equals %S. Now this is a static array. I don't have any issues here. Okay, has a price of % float and the stock is %D. This is what I like about printf. It's very flexible here. If you try to do this using output stream and concatenating strings, yeah, it's not so easy. Okay, so ID here it's p.code, p.barcode, p.price, and p.stock. Okay, and for the description, and here just add the \n. And for the description, we need to validate it. So if p.description different than null, we print the description. Printf \n description %s. Okay, and the print it, p.description. Okay, otherwise we don't print it because there is no description there. Okay, so every time you use a dynamic field, try to do a pattern out of this, always validate the pointers. Okay, so now let's compile this. Let's see if this is working. Build, rebuild. Okay, my usual problem, but I'm still not memorizing this value, and I will not do that. Okay, so define CRT secure, no warnings. Okay, build, rebuild. So in my case, that solved the problems with the SDL. Okay, and now we are here. So we can create, we can copy, and we can print a product. So now let's dive into the binary search tree. So the first thing that I want to do is to create a method that will allow us to create a new node. So like I said, the algorithm for searching and inserting and deleting is the same. Now, maybe for balanced binary trees, which means next week, I will go for the file, for the index, okay? Because there it's perfect. It's a balanced tree. It's the size, the height is controlled. It's perfect. So let's go today for the one with the storing, which means for this approach. And when we will move to AVL, we will implement this one. We will create an index. Okay, so we will also store the data in binary files. And in that way, we remember that part. Okay, so for today, let's go for this one. So the tree will store also the products. Okay, so here I need a function that will allow us to create a node. So bs node. And remember the rule that we established when we dive into the dynamic structures, starting with simple linked list. Every time you create a node of a simple linked list, double linked list of a tree or a graph, always return the address. We always manage those nodes by pointers, okay? Never by value, okay? So this should be a generic rule, because otherwise you can get easily into problems, because we link the nodes by addresses, but if you return me an article, sometimes that article could be on a function stack. And we know what is happening when the function terminates. The stack is destroyed. So you don't want to get addresses of things which are on a function stack. Okay, they are not reliable. They exist only if the function, only during the time that the function executes. Okay, so always return pointers. Okay, so create node. So here I want to create a node, and also I want to get a product D. So let's create a node. Yes, node. And once again, they will always should be in heap. Sorry. Okay, a new node equals binary search tree node malloc. And here is the size of a binary search tree node. Okay, multiply with 1, but is the same thing. Okay, so we have it. Now, even if we initialize them, I will always write also this part here, just to emphasize the importance of initializing the pointers. New node write equals null. Okay. And also now for copying, because we have a dynamic field here, you could easily use equals if you don't have dynamic fields in the structure. But because we have that, I will do this. So copy product. Where do we want to copy? We want to copy into new node product, the product that we get here. And now copy product needs here the address, not the address of the pointer new node, the address of the product. So in order to get it, and be sure you apply the address operator to the entire entity, I will write it like here. So this is ampersand of new node product. So here you get the product, and this is the address of that product, not the address of new node. Okay. So that will copy the product there. Okay, and return it. Return new node. So now we know how to create a new node. Okay. And now let's insert something in the binary search tree in order to have something to work with. So the first function that we need to create is insert. Okay. Now, if I will define here a binary search tree, this is the way I will do it. So binary search tree node. Okay. Let's say products. Okay. And here initially that will be null. And after this point, I will insert into this products binary search tree products, and after that we need to search for them. So this is the scope of a binary search tree. And in order to test that fast, we need here a method to print the binary search tree, and that will be one of the first recursive functions that we will write today. So here I need a function that will print products, print binary search tree. Print, yes. Now, when you print a binary search tree, because you have actually 3 ways of going through the tree itself. Okay, so if I switch to whiteboard, okay, let's suppose we have this this binary search tree. Okay, it has these nodes. I'm not insisting on the values right now, but it may look like here. Okay, when you start going through the nodes, okay, you always start with the head, with the root node. Okay, so this is the root node of the tree. You see, each time you have, if you want to print the tree, you have 3 possibilities. The first possibility is to delay printing the value here and moving to on the right side. Okay, so sorry, on the left side. This is how we see it. Okay, this is left, this is right. So you can delay printing the information, and you will always say, if I have the possibility to go on the left side, I will follow that path until I can't. And after that, I will print the value in the current node. So this is one possibility. The other possibility, the second one, is to print the value, and after that to move on the left side. And the third possibility is to not print the value, not go on the left side, but go on the right side. Okay, and after that, print the value and follow the left side and so on. So these are the three possibilities that we can use in order to traverse a tree, in order to print the values or search for values, because in the end, this is also the searching technique. And each these possibilities, they have a name. Okay, so the one that I will write some, so let's say this is left, this is right, and this is the current node. Okay, so I don't know, let's mark it with an asterisk here. Okay, so the first possibility, when you go and you follow the left path, and after that, when you return, you process the current node. This is it's called pre-order. I think I have here a text. Okay, so this is pre-order. Okay, which generally means left, current node, or let's say asterisk, we name that asterisk, and after that, right. Okay, so you will always follow, if you can, the left side, you will dive on the left side, and when you can't, you print the current node, and after that you follow the right side, and once again left, and so on and so on. We will do different traverses. Now, when you focus on the current node before following a path, left or right, this is called in order. Okay, and here you have the current node, left, right. Okay, and the third combination, when you are focusing more on the right side, it's called post order. And here is right side, current node, and left side. Okay, so these are the three ways that you can use to traverse the node. So you see, you give here different priorities to either the left side, the current node, or the left. So the left side, the current node, or the right side. So these are the name: pre-order, in order, or post-order. Okay, so we can choose either of those two. Now, for a binary search tree, the in order is special because it has this interesting property. If you traverse a tree by following the in order approach, you will always get the values like they were sorted ascendingly, for example. Okay, so by traversing a binary search tree in the in order approach, you will always get the keys like they were sorted. Okay, and because we have the properties between the keys of these three nodes. Okay, so which one do you want to use? Pre-order, in order, post-order? So which one do you think it's more relevant to see the tree? Anyone? So anyone having any? We can't flip a coin. There are three options. Okay.
Pre-order.
Okay, pre-order. So let's write this here. So print BST, just to know. Yeah, I can't use that. Pre-order. Pre-order. Okay, so pre-ordering means always try to get as much as you can on the left side, and if you can't, then you will print the current node, and after that, move to the right side. So what do we need here in order to print a binary search tree? We need a binary search tree. BS node, root node. Okay, so if root equals with null, we exit, return. Okay, if that's not the case, which means you don't have a tree or you reach a dead end, you reach a node. If that's not the case, so pre-order means go on the left side. So I will call this recursively, print BST pre-order on root left side. That will go as much as it can until it will actually reach a leaf node. It will dive on left. Left is null. It will return. And after that, it will execute the next instruction here, which is print product of root product. Okay, after the current node has been processed, it has been printed. Now I do a print BST pre-order, and here you move to the right side. Okay, and that's it. So this is the print BST pre-order. Now, if you get the idea, you can easily determine the other ones. For example, in order will be like this. You first process the current node, and after that you move on the left and the right. And I think it's simple to deduce the third option. You just define the other combination when the print product will be the last one. So it's left, right product or current node. So in this way you can traverse the tree. Okay, now let's do the inserting. So when we insert something here, we have two ways to do the insert. One is to return the, let's say, the current node, because let's suppose you have an empty binary search tree, which means the root is null. So if you insert something in that tree, the root will change. You'll have a tree with one node, which is the root. So you need to return it. So here we have two options. We either return the current node each time, or we pass the current node as an address. Okay, so you have these two options: void insert, and here you have the BS node, okay, which is the root node. But here, and the product that you want to insert, product B, okay, and in this way, how do you pass this variable in a way that the variable, the pointer itself may change? Just think for the special case where initially root is null, you need to initialize it with an address. So in that case, if you do that, here you need to pass a pointer to the pointer, because that pointer, which initially is null, will change. Okay, you need to have access to it in order to set there an address. So you need to pass it by address. So that's not a matrix. Okay, if there are two asterisks, it doesn't mean it's a matrix. It's a pointer to another pointer. So this is one version of doing it. And the other version, if you don't like this approach, but here you have other things to do, is always return this one. So you call insert on root. Initially it's null, but you always return it. So here is like products equals insert of products. And here is like insert of address of products. Okay, so that's the difference between two. So which one do you want to use?
Void.
The one with void. Okay, so I will leave this commented just to remind you that. And maybe for AVL, balanced binary trees, just remind me to go for this one. Okay, so you'll have to variance. Okay, so always start with the easy part. Okay, never dive into complex stuff. Okay, don't worry about that. Always start with the easy part. So what's the easiest scenario for us? Root is null. So if root is null, okay, yay, it's the easiest solution. Root, let's open a bracket here, a block. Root equals what? Create node of P. And that's it, return. Okay, now because this is a pointer, you see here it's very easy to do mistakes. Here we are checking the pointer to the pointer, but what we really want to do is to check this one. Okay, because here you get the address of the pointer. We want to check the pointer at that address, and also here. So in this case, you need to get the values. And I think you have already seen that if you miss this pointer here, the compiler has no issue with that, but you are checking other values. You are not checking what you should check. Okay, so watch out for this kind of stuff. if you pass here by pointers. Now, this version will not have this issue because here you remove the asterisk because you always return this variable, okay? So here you play directly with root. Okay, but like I said, we will cover that approach for the other ones. Okay, so this is the easiest case. You find yourself in a current node which doesn't exist, so you just created the node and return. Okay, now, if the node exists, it means you are here, right? Because otherwise return will terminate the function. So if you reach this spot, it means the current node exists. So the other easiest, let's say, scenario, because it's a binary search tree, remember, you will never accept duplicate keys. So let's check for a duplicate key because we don't accept this. Check for a duplicate key. So how do you check that? Now, what's our key? It's the barcode or the code. So we compare it with string compare or with equals equals. That's the difference. Barcode or code.
Code goes easier.
Code, it's easier because we don't need to write string compare, but the logic is the same. So there should not be anything different for barcode. So if root, and once again, you see the same problem with the asterisk here. So it's like here, but once again, here you need to be sure that you get back your pointer by using asterisk root, and now apply this one, because otherwise you may have problems with operators priority. The arrow operator can be applied before the asterisk, and once again you will check different values. Okay, so here it's root arrow product dot code equals p dot code. We have a duplicate. What do? Return. We don't accept duplicates, so you will not insert it. Okay, so in this case, sorry,
don't we update the product maybe?
yeah, we did that for the other. Okay, so let's say either return or exit, or the alternative will be to update. So if I want to update, we have a function for that. Copy product where into, once again, root. I want to be sure. You see, even the IntelliSense can't decide, hey, do you apply here to extract the pointer to root, or this is just a pointer. So that's why it's forcing you to write like this, which is a good thing. So copy into product P. Okay, and now we update the product at that address. But remember, copy product requires the address of this. So just to be sure that I apply the ampersand to what I need to apply. So in that case, it will be like this. Okay, so these arrows are assuring me that I apply the ampersand operator to the product from that pointer. Okay, so exit or update. Okay, I can leave this both functions. So this is how you will update the product. Okay, now if we are here, and I think the return should be here, because if you uncomment this, you should also return. Okay, so if you update, you should leave the return also and exit. Okay, so I think this will always happen. Now, once again, if you reach this spot, it means you didn't exit by this condition and you didn't exit by this condition. So what it means? It means that the code is different. You have P has a code different than the current node. So at this point, we need to decide on which path do we continue searching for a location to insert, left or right. So here we need a rule in order to say to us which path to decide, because flipping a coin doesn't work in software. Okay, you will never get reliable results. So what is the property that will always help us decide on which path to continue? So in a binary search tree, there is this rule that describes the relation between nodes in terms of values. And the rule is saying that if a node has this value, for example, 10, the left side node will always have a value less than. There is no equals. Why? Because when you insert, you don't allow duplicate keys. So there is no less or equal. It's either less or greater, and that's it. Okay. Here you can't have 10. So here you will always have values less than 10. For example, 5. And so the values are less here. And on the right side, you will always have values greater than 10. Okay. So I think it's quite the opposite. The relation is different. So here you have the values here, the relation between node and left side. Yeah, I will write it here to be more clear. So this will always be greater than left side. And here, so this was right. Here you'll always have values bigger, which means right values are always bigger than the parent node, okay, which is this one. So here you will have 20. And the relation will continue. So for example, here you will have a value less than 10 and less than 5, for example, 3. And here you will have a value greater than 5, but less than 10, okay? So the entire subtree behaves in the same way. So for example, 7. Okay, so let's see where I should insert the value 6. So 6 will be like here. 6 is less than 10, so I need to continue on the left side. 6 is greater than 5, so I need to continue on the right side of 5. And 6 is less than 7, so here I should continue on the left side. And here I will get a null pointer, which is our case here. Sorry, is our scenario here. When you reach, okay, a null reference, you create a new node and you set that address to the new node. Okay. So in that case, 6 will go here. This will be the location of 6. Okay. For example, 100. It's greater than 10, greater than 20. So 100 will be here. Okay. Now, let's say something less than 20. So this is 20. 15. 15 is greater than 10 and 15 is less than 20. So 15 will go here. So this is the relation between the values that will always help us decide on which direction we continue, when we insert or when we search, or even when we delete, because we need to find that location. Okay, so let's go back to Visual Studio. Okay, so here, if we are here, we know for sure that we didn't reach a dead end yet. We don't have a duplicate key. So here we need to check what are the relation between the current node value, the key, and the new value, the new code, new key that I want to insert. So if, once again, asterisk root, okay, arrow product.code is greater than p.code, sorry. So if the value of the current node is greater, it means we need to search for a location. So the current node has a value greater than p code, then the new node on what? On the left side. Okay, so we are here. It's like you are here, the current node has the value 10 and you want to insert 2. So we need to continue on the left side. Okay, so how do I do that? I call the same function, insert, and I will pass as the new, let's say, current node, the left child of the current one. How do you get that? Once again, asterisk root, in order to get back to the initial pointer, left, and now p, the same value p. And now insert here needs the address of that pointer. So once again, I'm writing this one here. Okay, so this is continuing to insert on the left side. Else at this point means is not equal, is not less than, which means it's greater. We already checked for equality and here. So the p.code value is greater than this one here. So in this case, we continue on the right side. So I will just copy paste this one here. And here it's right. Okay, so this is how you insert into a binary search tree using this approach. The difference from the alternative is that here you don't need to write root left equals or root right equals, but you see you need to use a lot of brackets just to extract your initial pointer again. Okay, so this
I
is
think
the
it's
insert.
easier to return it.
Sorry?
Right? Isn't it easier to return it to use the other method?
Yeah. In terms of code complexity, because the algorithm is the same. So
Yeah.
it's the same algorithm. Now, this looks more complex because of this, and it's more riskier. So here you can easily do mistakes. I just showed you one. So if you write this one here, now you'll have a very interesting bug. Okay.
Yeah.
Okay. So yeah, in terms of complexity and risks, I will go on this one, even if calling it means an equals. I will pay that price because here I can do much more easier mistakes. Okay. Now you have the two options. I think Mihai showed you an example with this approach. And like I said, next week we will cover it. So in the end, you will decide. It's the same algorithm. I don't care if you do like this or like this. Okay. The idea is to make it work. Okay. So let's test this one. Okay. Let's test the insert because we can print the binary search tree in order so we can easily test it. Okay. So let's test the method. Let's insert some products. Okay, so let's define a product P1. Okay, and what do we have here? We have we have init. So yeah, we have init product. So barcode 2AAB34, whatever. The description, nothing, empty string. Price 2.3, stock 100 items, and the code, let's say 10. Okay, and let's create this for yeah, I will name them like X20, and here I will set 20, 50. Let's add another one, and this is P2. Okay, so this one will be 3x3. Okay, the same values, it doesn't matter. Okay, and now let's insert them. So insert the address of products P1, and now you duplicate the key, the line, and you have P2 and P3. So let's have another one and one here, X1. Okay, so let's also add this one, and this is P4. And now let's print the binary tree. Okay, so print, let's see it in order, products. And after that, printf, \n, printf, and print it again, pre-order, products. Okay. So let's see if this works. Build or rebuild. Everything looks okay from the syntax perspective. Now let's see if this works. Control F5. Okay. And I have a very interesting exit code. I have no idea why. Let's run this again in the debugger. So F5. It will crash and it will lead me to this. So let's see. Exception thrown. I have an exception thrown, blah, blah, blah. Access violation reading location 0x CD, CD, CD. Now, CCC, it's something related with uninitialized pointers, but CD, 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 it's a value that generally you will see for free allocated memories. Something, it's like when you call free, you get that, that address. So let's see where we are and how we reach this point. So we are here in copy product. Let's see the source. And the source is code 10. And I think this is the first product. And here the destination is a pointer that you see for the description. It says 0x CD, CD, CD. And we are here. Okay, so the destination description is 0xCDCD, which means it's not null, and we try to free that up. Now, let's check the call stack. And I think we are here on create node in insert. Okay, so we reach that spot here after create node. So when we have created the node, so this is the new node, it's null, null, left, right, and the product here has the description 0xCCD, and we want to copy it. So the problem is that the first time we create a product, when we actually create the node, the new node product description pointer is 0xCDCDCD. So it has been initialized, but you see, is not taking the null from here. Okay, it's not taking this null. So here, when we create the new node, when you allocate space, you get a binary search tree node. We make the left and right pointers null, but inside the product of that new node, okay, we have a product article there, the pointer description is not null. So it didn't use the initialization that I have provided here. Okay, so in order to be sure, that's why I'm writing twice those initializations. In order to fix the solution, we need to initialize that pointer ourselves here. So new node product.description equals null. Okay, so when you get a new node, now we know that the description is null. So it will not try to free it, because in this case, we avoid staying with the default value 0xCDCDCD. It's not CCC, but it's still related with that value because you have seen it's CDCD. Okay, let's try to give another, let's try it again. So build rebuilds.
How did you realize that the problem was there? How did you use that call stack?
So let me show you again, and let's go step by step. Okay, so I will comment this again. Yeah, so let's run it together with F5. Okay, it will crash here, and generally it will crash on the instruction that generated the thing that it should not supposed to happen. So the first thing that I check is where we are. So we are in copy product. Okay, and we know that copy product, it's a function that we called several times during the code. Okay, if you go for find Control F, you will see that we call copy product several times. So in this case, we know the problem is in copy product, but the next question that I have is, okay, how did we reach copy product? Because we have several places where we call it. Okay, because sometimes the problem is not the function itself, is the values that it gets. And this is what I'm searching now. So let's see, we are in copy product, and you see the error is here. And now reading the error, the runtime error message, access violation reading location 0xCD/CD. Okay, so this is one information, but sometimes it's more reliable to check yourself the values of the local variables. So let's see. This is the instruction that generated the runtime exception. And if you hover the mouse over variables, you will see their value at this precise moment. So what I'm seeing here is that at this point, description is 0xCD/CD/CD. So this is another address, let's say specific to Microsoft compilers. And like 0xCCC, you will never get to that address. So trying to use it or release it will always end up in this kind of scenarios with a runtime exception. So at this moment, I know that the description here is 0xCD/CD. So my question now is how we reach this point with that address there, 0xCD/CD. So let's check the input arguments, okay? So I know it's a field from destination. Let's check destination. So I'm checking the destination and I see it's 2AB34. I see the code, I see the price, so check the other variables. They look okay. And from this information, I know for sure that this is something we received. So copy product received a destination here that has the description 0xCD/CD/CD. Okay, now let's check the source. Now the source is okay. You see 10, the value stock. Remember, for floating point, you will never see 2.3. Okay, it's always an estimation, so don't worry about this one. Okay, here the description, it's okay. It's an empty string. So because I know that copy product, it's a function that we called from several locations. Now I want to know which is the path. How did we reach this? And the only tool that you have right now, other than running again the code line by line, and you will waste time, is always check the call stack. Okay, the call stack is that relation between the function that called the function that called another function which called copy product. So in this way, you know how you reach this place. And now you can check what has happened in the parent function, the one that called copy product. Why do you get the destination with the description 0xCD/CD? So now you do a reverse engineering. You follow the trail backwards. Now, if you don't see the call stack here, all these windows can be activated from debug. Debug windows, here they are. Okay, call stack, threads, modules, memory, they are all here, locals. So if you don't have the call stack here, you can activate it by here, debug windows, call stack. So now if we see the call stack, okay, always search for the last instruction, which is from your source code. Because you see, actually, we reached this spot. This is the location of the runtime exception. You can't search for answers here in the DLL. So always go from top to bottom, because this is a stack. That's why it's called a call stack. And always find your functions, the functions that you control. So right now we are here. You see in seminar 10 exec copy product, and it's giving you the line 47. You see, it's line 47 in my case. Line 47 is the free. So how do we reach copy product? You see, create node is the parent function, the function that called us here. So in order to reach this line 64, and also to check values, always double click. So if you want to see what has happened in create node, in order to determine why you got the destination with the 0xCD/CD pointer to value to the description pointer, double click here functions. So if you want to see what has happened here, double click create node. And now you are here in create node who called copy product. So you see here we are passing the new node product. And if you check the new node, you see that when we created the new node here using malloc, the right and left are null, but inside the product, the description by default received this. It has ignored the null that we have defined it here. Okay, so this is not used for here. Okay, so that's why I realized that the problem is here. The product that we get in the new node has a 0xCD/CD value for that pointer. So stop debugging. Okay, now we fix it. We know it's a new node, so normally the description pointer should be null. Okay, so let's try again. Build, rebuild. Close the XA if it's still open. So Control F5, and now everything should look okay. So let's see. And that's why I always do a new in order or a pre-order. Okay, so for example here, this is 1, 3, 10, 20. So I think this is the in order. Let's see. Yeah, I think I messed them up. The in order, yeah, sorry, it's not the in order. My mistake. Sorry for that. The pre-order will give you the values ordered. So this is the pre-order. Okay, sorry for the mistake. And this is the in order. So we inserted. Let's switch back to the to Visual Studio in order to check if everything is okay. So we inserted 10, 20, 3, 1. So if I go back to the okay, so sorry for this mistake. Here is the pre-order will give you the values in so you get values ordered or sorted, sorry, sorted. Okay, the pre-order one. So let's draw fast the tree again. So we had 10, 20, 3, 1. So 10.
We still see the Visual
Yeah.
Studio.
Okay, thank you. Sorry for that. Thank you for alerting me. Okay, so we started with 10. 10 is the new node. And after that, we inserted 20. So 20 will go here because it's bigger than 10. Okay, and after that, we inserted 3. 3 will go here because it's less than 10. And the other node, the last one was 1. So 1 is less than 10 and is less than 3. So 1 goes here. Okay, so if we go through this array in different orders, let's add the text here. Sorry, text. How do I move it here? Okay, I want to move it here. Okay, so the pre-order will be, remember, always left. So left, 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 you reach 1. So left, 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 return 1. Okay, and after that, right, nothing here, go back. Go back to 3, 3, go on the right. Is nothing here. Go back to 10. So 10, continue on right, left, there is nothing here on left. Go back to 20, try on right side, there is nothing there. Go back and return. So this is the pre-order for that tree. Now in order, let's see, always process the current node. So here you will have 10, process it. Move to the left side, 3, process it, 3. Move to the left side, 1, process it. And after that, left, nothing, go back, right, nothing, go back, 3, right, nothing here, go back, 10, go back here, 20, process it, left, nothing, right, nothing, go back and go back. So this will be our in order 10, 3, 1, 20, and pre-order, you should see them order or sorted. So this is a check for binary search tree in order to be sure that you created the binary search tree correctly. So if we switch back to our input, so just keep in mind the pre-order one, the in order, sorry. So it's 10, 3, 1, 20. So 10, 3, 1, 20. And this is the pre-order which is sorted 1, 3, 10, 20. So it means that we created the binary search tree. Okay, so this is the proof that it has been created. Okay, Okay. And if you have, let's say 5 minutes, how do we do a search? Okay, so how do we search for a node? Because that's the scope of a binary search tree, is not to print it. Okay, we just print it just to show that everything is okay. And also here you should normally do another test, trying to insert a duplicate key, for example, in order to be sure that that will not happen. Okay, this is another normal test for a binary search tree. Always try to see what will happen if you try to insert a duplicate key. Okay, like in this case. So the last function that we'll implement is the search function. So a search function should do what? Return a product, search, into a binary search tree node based on a key code. Okay, so this is how you search for something. Now, when you search for something, nothing will change inside the tree. Okay, we know that for sure because you don't change anything there. So that's why we don't need to pass anything by address. Okay, so once again, it's a recursive method. And we know that at some point we will return this result, product result. Let's initialize it. And also here, in order to say that the value is not there in the binary search tree, we will use a logic value. For example, we return a result with the code -1. And this will be our way of saying there is nothing there. So we need a product with empty barcode, empty description, price 0, stock 0, and code -1. So this will be our result that we can check after we call search in order to see if we found something or not. Okay, so after this moment, once again, always start with the easy part. So the first thing is what will happen if you search into an empty tree or you reach a node which doesn't exist. So if node equals null, return result. Okay, so this is it. Now, if you reach this spot, it means the node exists. So in order to search that, we will use the relation between the values in a node and the values in its siblings. So once again, we compare. If code equals with node.product.code, we just found it. So copy product into result, the source, and this is node product, and that's it. Okay, and open the brackets here. You found it, return it, return result. Now else means they are not equal, but else means maybe it's less or greater. So always check for that. Don't assume things here. This is a common mistake. If they are not equal, it doesn't mean it's greater. You need to check that. Or if it's not greater, it doesn't mean if they are equal. It doesn't mean they are equal. It means equal or greater. Always check all three possibilities. So else, if code greater than node product dot code, it means we need to continue the search. So code is greater, the current key is the key for which we are searching the product is greater than the current node key. It means we need to continue on the right side. So once again, here you see a search and we continue on the right side, right, using the same code. Now, what will happen here? The search will dive into the tree. And at some point, maybe you will find that product. So another call of search will find it and it will return result. Who will catch that result? No one. So you will lose it. So why? Because you see, you started with the root node, you continue to search on the left, on the right side, and some point you will find the product, you return it, no one is catching it. So here, this is like the fireman approach for it's the fireman bucket strategy. You have a row of firemen, and they pass the bucket with the water from one to another. So the last fireman will throw the water on the fire. Okay. Now what will happen with the bucket? The bucket is sent backwards to the beginning of the row in order to be filled up again with water. Okay. And this is how you need to think recursion. If you have a function that is returning something and you call that function again and again and again, so you create a recursive algorithm like here, you see it's returning a product, always happen, what will happen with the result when you return it? It's like the fireman will throw the bucket. So you will have no buckets. How do you put out the fire? So in this case, pass the bucket again backwards to the beginning of the row. So here you have this return search. So at some point you will hit a dead end. Here you return this empty result, and the previous call will get that result and return it again. So now the result is coming back, okay, to the initial call of search. And here else means return search of node left code. Okay, and this is it. This is the search algorithm, okay, in the recursive manner. Now, if you feel that recursion is a problem, you need to start doing simple examples, because from this point on, most of the functions that we will write are recursive, okay? And this works for trees and graphs, okay? So the last weeks are based on recursion. Okay. So this is the search. Now let's test it. Build, rebuild. Okay, so let's test search here. And I will have product result equals search of products. And let's search for 3. Okay, let's print it. Print product result. Okay, so Control F5. Okay, here I'm checking also to see duplicates. I don't see them, so insert is okay. And you see product ID 3, barcode X3, price, stock is 50. Empty description. Okay, but we have a string there. It's an empty string, but you have it. Okay, so let's try to search for an object that doesn't exist, a product that doesn't exist, to see if we cover that part. So for example, here, I will search for 300. So once again, result here, Control F5. Okay, so you have it here, ID -1, no barcode, no price, not stock. Okay, so at this point, if you check the result code, if it's -1, you know that you don't have any product in the binary search tree with that key. Okay, so this is the way we can notify others about the search result. Okay, so you have seen insert, print, and search. There is only one method that we need to cover, and that's delete. I think Mihai showed that to you during the course. The problem with delete is that it may generate very strange scenarios here inside the tree. So for example, what will happen if you try to delete 7? Okay, now when you analyze delete inside the binary search tree, there are actually 3 possible scenarios, and you always start with the easier one, and the trick here is to try to make the most complex scenario to transform it in one of the easier ones. So the three scenarios are this. If you try to delete 6 or 15 or this node, that's easy job because all these nodes are leaf nodes. What's a leaf node? A leaf node, it's a node that has both right and left siblings null. So it means it has no siblings. So deleting this node, it's simple because you just delete it, release the space, and the only thing that you need to make to do it is to make sure that this pointer now becomes null. Okay, so this is deleting a leaf node. It's easy. The second scenario means to delete a node that has at most a sibling. For example, deleting 7, or I think 7 is the only one, or 20 after you deleted 100. So let's focus on 7. Now, if you delete 7 and release the space here, so this node disappears, the question here, what's happening with that sibling, the left or the right side one? Okay, what will happen with it? Because at this moment, it's up in the air, okay? It's not linked with the rest of the tree. So this is the second scenario. The node that you want to delete, it has 0 or at most 1 sibling. And here it doesn't matter if it's the right or left. Why? Because the solution here, it's easy. You delete the node, you release the space occupied by this structure, and you make the link of the node of the parent of the node that you deleted to point now to its unique child. And like I said, it doesn't matter if the unique child is the left child or the right side child. Why? Because let's think for a moment. If you delete this node, this is a subtree. All its child nodes will have values either less than 7 or bigger than 7. But because 7 is on the right side of 5, it means all the nodes here are bigger than 5. It doesn't matter if they are less than 7 or bigger than 7, they are all bigger than 5. So at this moment, like I said, it doesn't matter if this unique child is either the left or the right side one. You just need to make this link to reconnect to that unique child. It doesn't matter which one is, but you know for sure you have one child. This is important. Now, what will happen if you want to delete a node that has both childs? And now this is a problem because the node will disappear and now you have two subtrees remaining up in the air. They are not linked anymore with the tree. And you have only one available link here, which is available because you just deleted that node. So how do you link two different nodes using only one link? You can't. So in this way, in this case, the trick is to transform this third scenario, which is the most complex one, in one of the previous two ones, the previous two scenarios, which were easier to handle. How do you do that? So if I, let's say, draw another tree just to exemplify the story again. Okay, let's say you have this one. And now you want to delete this one here. This one here. You see, you have only one available link, but you have two nodes, the two childs, which one do you link using a single available link? Because you can't link both of them. So in this case, you don't need to delete this one. So the trick is to transform this case into the first case or the second one. So the trick here is not to delete this node. Okay, you don't want to do that because otherwise you have two other problems. So at this moment, you don't delete the node, but you replace its value. You want to keep this node in place. You want to keep it linked with all the other nodes that exist at this moment. So you want just to replace the value. So which value can you put here in order to keep this tree a binary search tree? So in order to do that, you have two choices. One choice is to replace the value here with the maximum value that you can find here on the left side subtree. So from this one, you choose the max value. How do you choose the max value from the left side subtree? It's very simple. You go on the left side, you reach this subtree, and now you go as much as you can on the right side until you reach a node where its link to the right side is null. That's your maximum. And this has been proved. So if you follow, starting with the root, the right side until you reach a node that has a right link null, that's your maximum in a binary search tree. So you take the value from there. Let's see, is this value. So you put this value here. The node is still in place. So now this node should disappear. Is this case the first or the second one? Yes, because if this is the node that gave you the maximum, it means that the right side link is null. This is the way you find it. So it has what? Maximum one child. So the left link is either null or different than null, but it doesn't matter, because if you delete this node, so if you have here another node, for example, this is case 2. You delete this node and now you make this link point here. So you see, this is how you convert the third scenario, which is the most complex one for delete into either 1 or 2. Now, if you want to go on the other side, for example, you want to use this subtree, here you are choosing not the maximum, but the minimum. You choose the minimum value. So how do you get the minimum value from a tree? Starting with the root, you will always follow the left side link until you reach a node, and that node left link is null. Okay? And in that case, once again, you get to a node, you take its value, you write the value here, and that node, because it might have the right side link different than null, so it means it might have a right sibling or none. Once again, you do the physical deletion there. Okay, you delete that node physically by scenario 1 and scenario 2. Okay, so in order to implement delete, you need a function that will give you max or min. Okay, at some point you need to choose either max or min. So now you can flip a coin. Okay, it doesn't matter which one. And after that, you find the node that you need to delete. And here is an issue. You see, when you find it, this one or this one, in order to reinitialize, to change this pointer or this one, you need also to be here. Because if you want to change this pointer to a different address, this is the place where you should be. So when you delete a node, you need to find the node itself and also its parent. Okay, because you need that for scenario 1 or 2. Okay, so that's delete.